In 7.5, we're doing hypothesis testing for variance and standard deviation. The overall concept is going to be very similar to all the previous chapters and videos, where we're going to look at a sample, and if that sample is really far away from the bulk of the data, if we're way out in the tail, then we're going to reject the null hypothesis. The main difference in 7.5 here is our distribution is going to follow what's called the chi-square distribution. You can see what it looks like here. It's not quite symmetric. It's kind of a little skewed to the right and oddly shaped. But the overall concept's exactly the same. When we look at our sample test statistic, if it's way far out in the tail to the right, or if it's way close to the tail here to the left, that is when we're going to reject the null hypothesis. The first few problems are about finding the critical values that mark the cutoff of the rejection region for either right-tailed, left-tailed, or two-tailed test. So let me show you how to do that in Excel. To find the critical values for a chi-square distribution, you use these formulas here. Put an equal sign in front of them. You need to know what probability you're looking for to have a cutoff of that much probability in the tail. And you need to know the degrees of freedom, which is based on one less than the sample size. So for example, let me jump back to the homework. If I want the critical value for a right tail test, sample size 20, and I want 5% to be in the tails, I would do the right tail test here. So equals chi-square dot inverse dot RT for right. I want 5% in the tails. And just to make sure I forgot, their sample size was 20, so our degrees of freedom is one less than that, 19. That gives you the cutoff mark, the critical value, where there would be 5% in the tail. If you're doing a left tail test, you use this formula here, and they'll give you the cutoff mark for having a certain percentage in the left-hand tail. And now a two-tail test, we don't have symmetry in the chi-square distribution. We're not quite symmetric here, which is different than the normal distribution or the t-distribution. So we're not going to have the same numbers for our critical values on the left side and right side. Remember, in those other distributions, if the one critical value was negative 1.9, the other one was positive 1.9 when we were doing a two-tailed test. Here you're actually going to want to do this separately for the left and right tails. So use this formula for the left and this one for the right. One big thing to keep in mind, let's use this example I was just working with. If I wanted 5% in the tails in a population of 20, my degrees of freedom is 19, but 5% in the tails, if I'm splitting that between two tails, I'm going to have 0.25 or 2.5 in each tail, 2.5%, or as a decimal, 0.025. So you would need to enter this to get the critical value for the right side, and then for the left-hand tail, chi-square dot inverse, I want again 0.025. And my left-hand tail, same degrees of freedom. And so you see we get very different critical values, but they are the cutoff marks. If we get any test statistic less than this value further left, that's in the rejection region. Anything bigger than 32 further to the right is in the rejection region. Here's a good picture of that. And 1, 2, and 3 are all using those formulas to find critical values. The next couple, you're actually just going to be given a critical value. And it's stated up here. This one says 21.0260. I don't know if that's too small to read. But that's our critical value, 21. So any test statistic that's larger than 21 further into the tail would end up in us rejecting our hypothesis. So you go through and see if any of these would be rejected. And for a two-tailed test, you would do anything bigger than this critical value or anything smaller further to the left than that critical value. So look through and see if any of those numbers fit inside the rejection region, and if they do, you reject the null hypothesis. Number 6 here, we're looking at a story problem, and this gives a good example of how this material can be used in the real world for quality control. We have a snack food manufacturer is estimating the variance on the number of grams of carbohydrates in the serving of its tortilla chips is 1.37. So you've probably never thought of it before, but when you get that bag of potato chips, it tells you how much carbohydrates is in there. It's going to vary from bag to bag. It's never going to be exactly that number. But the manufacturer works hard to control it, so the variance is small and it actually stays pretty close to that number, and the consumer can trust the value. And the FDA and other organizations can monitor that by using this sort of test to make sure the manufacturer is actually meeting that goal and keeping us close to how much nutrition they say is in their product that they're making. So in this example, a dietitian is asked to test the claim and finds that a random sample of 19 servings has a variance of 1.34. So it's a little different than what the manufacturer was claiming. So at alpha being 1.01, is there enough evidence to reject the manufacturer's claim? So we always need to start off with our null and our alternative hypothesis. The null of the claim here is that our variance is 1.37. So our alternative is just that it's not that it's something different. So find the critical values, the rejection regions. We're going to use those formulas we just looked at here in Excel. And so for the left tail, we want just 1% in the tail. So I'm taking 1% and dividing it in half. We have a not equals to for our alternative, so it's a two-tail test. So divide how much we want in the tails in half. Our degrees of freedom is 1 less than the sample size. So again, we're dividing that percentage between the two tails. We had 19 in our sample, so 1 less is 18. So that gives us our left tail. And again, for the right tail critical value, divide the 1% in half, divide it by 2, and 18 is our degrees of freedom. So if we get back a test statistic that's less than 6 or bigger than 37, that's when we're going to reject the null hypothesis. Now here's how you find the test statistic for our chi-square distribution. You're going to take the degrees of freedom, 1 minus the sample size, multiply it by the variance of the sample, and then divide by the variance of the population, or what our null hypothesis is. So in Excel, I do my 18 times the variance from the sample, and it was just stated that's what the dietitian found, and we're dividing by our null hypothesis that the variance is 1.37, and so we get 17 point some decimals here, 17 safely in between these values. It's not further out in the tails, so we don't have enough evidence to reject the null hypothesis. So 7 and 8 are going to be similar to what I just showed there. You need to start off by just coming up with the null and the alternative hypothesis. Find the critical values using these formulas. And then we're going to have to find the test statistic to see if we should reject the null hypothesis or not. So pay attention to some of the little nuances. Make sure you know if you're doing a two-tailed test, if we're just looking for not, or if it's the left-tailed or right-tailed. And that'll help you know which of these formulas to use for your critical value. One thing that is different about, and one thing to look at here at the last problem that is a little different, is we don't have the sample standard deviation or the sample variance given to us. We actually have the real data from the sample. So you need to copy that and put your sample in Excel, and then you can use variation.s and select your sample, and that would give you the sample variance. Or you could use standard deviation.s if you were going for the standard deviation, and again select your sample. And so I recommend going with variance, just because when we're going to use our formula here, we need to have the sample variance. So we would plug that in. Another, I guess, pointer to always remember to think about is this is variance, So if the problem would list the sample standard deviation, Like, let's take a look here. I think number 7 might do that. Yeah, and number 7 does that. It tells you what the sample standard deviation is. But when we're using our formula, we want to use the variance. So you would need to square that value, make sure you're working with the variance here when you're finding the test statistic. So going back, let me wrap up number 8 here. And I think I probably have different values here since I flipped and went away. But the process, finished wrapping up talking about that. You have to find that on your own by using the actual data values on your own. You have to find the sample variance. And then notice what we're given here is the standard deviation is what the claim is. The standard deviation is equal to a certain value. So again, plugging that in to the formula, you're going to have to square that because we want the variance claim, the null hypothesis, the variance of the population. That's what we divide by here. So we would do a little bit of conversion then. And then take your sample size, -1, your degrees of freedom, multiply it by the variance you get from your sample, and divide then by the variance of the population, which is the null hypothesis. And that's how you get your test statistic.